Okay, as I said in today's lecture, we will look at a very simple formulation for a simple problem. How do we do a mathematical formulation for a simple problem? And then we will, if time permits, we'll try to also look at how do we solve it graphically. So look at some basics for the linear programming. How can we solve it graphically? What are some of the properties of a linear program from a geometry perspective using a problem we call GTC, which is already on Moodle. So you should have the file, Excel file for that problem on Moodle. Take a look at it. I actually placed a bunch of files on Moodle, Excel files, which we will use today and next week. So take a look at them. Graphical sensitivity analysis. So we'll, after the graphical solution, we'll look at some sensitivity analysis, and then we'll deal with this next week. How do we solve the problem using Excel for those of you who don't know? And then we will talk a little bit about the add-on that comes with this book. We'll see if it's still available or not, and how do we download it. So, as I said last time, there are two kinds of operations research models: deterministic models and stochastic models. The deterministic models are those that use or assume that the quantities that they use in the formulation are known with certainty. So they are deterministic, certain, and the objective of those kinds of problems or models is usually to optimize a certain quantity. Optimize meaning either minimize or maximize. And usually we talk about either maximize profit or minimize cost or minimize some kind of a risk, and so on. On the other hand, the stochastic models, which we will not discuss in this course, obviously, usually require knowledge of probability because they use quantities. The quantities used in the formulation usually are expressed in probabilistic distributions. And normally, the objective of such models is usually to understand or estimate the system performance rather than to maximize or minimize the quantity. Okay, so how do deterministic models look like? Most deterministic operations research models can be formulated as mathematical programs. Okay, and mathematical programs, the word program is not similar to what we know as computer program, let's say like code. However, program in the context of mathematical programs mean a set of instructions or a set of equations or a plan. So when we say mathematical program, we do not mean any programming, computer programming. It's just a bunch of equations. That's what's meant with programming. Okay, and so the mathematical program or the model, the mathematical model, you can call it instead of a program, usually consists of a bunch of equations or inequalities, and they look like this. We have a minimize or maximize, a quantity z, which is a function of a bunch of variables, which we will call decision variables. I will define these more carefully in the next slide or so. But for now, let's just imagine that this z is a function of a bunch of decision variables. There are n of them. And there are also other functions involved in this mathematical model, which we call them constraints. And again, I will express these or describe these better in the next slide. And these functions are, there are m of these functions, gi, I between 1 and m. So that means there's a g1, g2, all the way to gm. There are m of these functions, and they are different than this function, the f function. They are called g functions, and they're functions of the n decision variables. And we call these constraints. And okay, so there are n of these variables, which I said I call them decision variables. So that's how would a mathematical program look like in general. As I said, those variables, the n variables we saw in the previous slide, which define the function f and the functions g, are called decision variables. These are the variables under your control, and I will again discuss later in this lecture why they are called decision variables. And those G functions are called constraints, technological constraints, structural constraints, functional constraints, whatever you want to call them, are all called the same. And that function f of those n decision variables that we need to minimize or maximize, which is the goal or objective of the mathematical model, and thus we call it objective function. And those various set of constraints that describe xj larger than or equal to 0 are called non-negativity constraints. I will revisit all of these actually in more details throughout this lecture, so don't feel frustrated yet. So in the previous slide, I talked about a mathematical program, which is a general representation. A special case of a mathematical program is called a linear program or a linear model. Okay, a linear program consists of a set of equations that are linear. Okay, so linear functions. So all what we talked about, the f function and the g functions, those functions are linear, which will make this program or this model as linear model, and thus the name linear programming or linear. Okay, so linear programming then involves the use of equations or inequalities or the use of mathematical functions that are linear. Linear, for those of you who know what's linear from high school or from freshman math or algebra, you're going to see that a linear function is usually consists a linear function that involves those n decision variables would usually be a linear combination of these n decision variables. So C1, C2 until Cn are coefficients of these decision variables and decision variables, and they are constant. They are known with certainty. They are deterministic quantities. Okay, and same thing goes for the constraints. They are also linear. Okay. And then we can see those last two sets of equations or inequalities actually. Xj, the decision variable, is less than or equal to uj, just like an upper bound on the value of this decision variable, and this is a lower bound. The non-negativity constraint is a lower bound. That means it is, we call it non-negativity because that means the decision variable cannot take negative values. It could be 0, so it's not positive, it's strictly positive, but it is non-negative, so it could be 0 or positive, and that's a lower bound. Okay, there are few properties that those linear functions must satisfy, and again, they're straightforward. For example, the contribution of each decision variable, here they call it activity. Also, the contribution of each decision variable to the objective function is proportional. So it's Cj xj. So the contribution of xj, particular x, let's say x2, the contribution of x2 to the objective function is proportional to its value. So whatever the value of x2 multiplied by this constant Cj. And also the same thing, its consumption or its use in the, it's what I mean by its, I mean the decision variable. Its use or consumption in the constraints is also proportional to its value. That means it's multiplied by this constant, Aij. Okay, so that's, so the contribution of the decision variable is proportional to its value. So that means, it has a constant coefficient in the objective function and in the constraints. There are no nonlinear terms in general. I mean, cross terms are nonlinear, but they're also, x1 divided by x2 is also not allowed because that's also nonlinear. E to the x1 is not allowed. So all of these nonlinear terms are not allowed. And that's by definition, we said this is a linear function. So all these nonlinearity or nonlinear terms are not allowed in the formulation. Otherwise, it becomes nonlinear optimization and nonlinear mathematical program, which we will look at later on throughout the semester, later on in the semester. Fractional values or decision values are allowed. So that means, if x1 equals 0.17 or x1 equal 7 over 12, it's fine. These fractional quantities are allowed. So, that means those decision variables are not integers. And if they are, then this becomes an integer program, which we will also visit later on in the semester. But for now, there's no such restriction on the values of these decision variables. And we already mentioned that those variables, the CJs, the AIJs, which are the CJs are the coefficient of the decision variables in the objective function, and the AIJs are the coefficient of the decision variables in the constraints, and the BIs are the right hand side of the constraints, and the UJs are the upper bound on those decision variables. All of these are known with certainty. That means they are deterministic quantities. We know their value exactly. It's not that we express them in terms of certain probability distribution. Okay, nonlinear programming and integer programming are needed if any one of these various assumptions or things that I mentioned in this slide and the previous slide I violated or do not exist. That means this becomes either an integer program or a nonlinear program, which is not what we're studying now. Now we're only looking at linear programs, and also stochastic models are not included. This becomes a different topic. Okay, now let's look at the nitty-gritty details of building a. Yes, sir. Go ahead, Ali.
I have a small question. When we say integer problem, can we take the binary problem as one of the integer problems, or it's a specific one?
What do you mean binary problem?
Yeah, it's either 0 or 1. So
what is it? What are you talking
okay, about? Sorry. So the coefficient or
what coefficient?
The coefficient to like in the objective function we have the C1 X1, for example.
Hey, I told you they can be anything. The CJs, XJs can be anything. The CJs can be anything. When we say integer, I'm talking about the decision variables, the XJs.
Okay.
Okay. And if the XJs are either 0 or 1, then this becomes a binary, which is still integer.
Yeah, I mean, can I take it as an example just to understand it? Because I'm familiar with the binary problem, so I wanted to understand it in that way.
Okay. Whatever makes you
happy. Is binary a particular
binary is
example?
Binary is integers. Binary is X will take values of 0, 1. Those are integers. Or it can X values of 0, 1, 2, 3, 4, 5, 6, 7, 10 million. Those are integers. Thank you, Ali, for your question. Yes, you're right. But we will visit these integer kinds of problems where the decision variables can assume only integer values or binary values. This becomes a different problem that we deal with it differently. Okay, for now, no. So that's why I asked you specifically what you mean by those. When I talk about integer values in the previous slide, I meant, I meant the values of the decision variables. But when I talked about being deterministic and known this with certainty, I was talking about the coefficients, the CJs, yes, and the AIJs. But this has nothing to do with making the problem linear or nonlinear. When I talked about cross terms are not allowed, that x1 times x2 are not allowed, yes, that will make the problem nonlinear functions. Okay? But at any rate, what's important is to remember from your linear algebra or from high school math, as I said, is what is a linear function. And a linear function is simply when a linear function of a bunch of variables in general, doesn't have any decision variables. Let's say you have 5 variables, x1, x2, x3, x4, x5. A linear function of these variables will be a linear combination of these variables. That means you multiply them by some constants and you add them together or subtract, and then you get a linear function. Anyway, so thank you again. Let me move on then. So as I was saying that to begin with, let's look at a very simple problem where we try to build a mathematical model or a mathematical program, specifically a linear program. That means we're going to be only using linear functions for a simple problem, which will better teach us what do we mean by those decision variables and functions, f, objective function, and the constraints. Okay, so this is a very simple problem. This is the simplest problem we're going to ever see. And the problem here says that there's a company that produces 2 types of. Well, before let me stop for a second and ask Did you don't forget to email me, guys, the grouping. I already received 2 emails for 2 groups, so I need the rest of the groups by next week. Okay, so don't forget that. And also, Omar, you were taking attendance, right, today?
Yes, doctor. Attendance and participation also as
That's
requested.
very good. Okay, right. Okay, let me say that this company, in this example, a company produces 2 types of products, wrenches and pliers. Those products use a common raw material, which is steel. So these wrenches and pliers are made up of steel, and they use whatever steel, different quantities of steel. For example, the wrenches use 1.5 pound or kilos or whatever you wanna the unit is. In this case, pounds, because here we have pounds. So we use 1.5 pounds of steel to build a wrench. Obviously, that's a raw material, and then you have somehow process it. And you also use some common machining, some common resources like a molding machine. So to mold the steel, and then some assembly machinery. Okay, so those are the 2 processes are used. So on the other hand, the plier will use only 1 pound of raw steel, and it uses 1 hour, let's say, because this is an hour, 1 hour of molding time on the machining, on the molding machine, and half an hour on the assembly machine. There are limited resources available to this company. For example, we can only have 15,000 pounds of steel available. I'm not sure if this is weekly or daily. So let's say we are assuming this problem is weekly. So there are only 15,000 pounds available during a specific period. And there are only 12,000 hours of molding machine time available. And there are also limited quantities of assembly machining time, which is 5,000 hours. That means you cannot have, basically you don't have an unlimited amount of resources. Okay, so you are constrained with such resources. That means you cannot produce an infinite number of wrenches and pliers. Anyway, even if you can produce an infinite number of wrenches and pliers, you don't want to do that, because you also have a bound on the demand. You cannot sell more than 8,000 wrenches and 10,000 pliers. So that's our objective. So we want to produce this much of wrenches and this much of pliers. We can want to produce more than that because we cannot sell it. And contribution, which is the unit profit for each one of these products, is 40 cents on the wrenches and 30 cents on the pliers profit. Okay, so here in this problem, the objective or goal is to be able to figure out how many wrenches and how many pliers to produce during this period, let's say during this month or this week, such that I want to maximize my profits. And you are asked to build a mathematical program, a linear program, for this problem in order to answer this question of how much to build, how much to produce from wrenches and pliers. Obviously, at first look, if you see here, there's 40 cents profit per wrench, so it means you're making more money on the wrenches. So why don't I produce only wrenches? Well, that's a good point. However, the quick answer to that is that you cannot sell more than 8,000, and maybe you have more raw material to use in producing the others. Okay, so maybe one strategy is to let's cap out on the wrenches because we make more money on them, and whatever is left in raw material, we'll use it to produce pliers. That's a possible strategy. It's not an optimal strategy. That means it's not the best you could do, and we'll see that later. Okay, any questions so far? Okay, so that's the problem. I'm going to use it as a context for our discussion or explaining the different parts or pieces of the linear program. As I said, the anatomy of the linear program consists of 3 things. decision variables, which are those are the things under your control. We seek to determine them. Those are called variables because they change, and they are called decision variables because I decide on them. They are under my control, as opposed to, let's say, random variables, for example. Anybody knows what is a random variable? It is a variable, apparently. That means it changes. Let's say a random variable that expresses or that describes the rainfall in Beirut, how much rain felt or last, a year, or what's the average rainfall, or what's the rainfall distribution of rainfall in Beirut. You're gonna say that it's a random variable, with an average so and so and standard deviation so and so. But what's the actual, how much rain is gonna rain this year? It's some value, it's a random variable, right? So what's the difference between a random variable and decision variable in this case?
The decision variable, we can control it, but the random, it's out of our control. صح؟
برافو آلاء. بس also in what ways it varies, this random variable? The decision variable is under my control. صح, I change it.
I cannot know what will it be.
Okay, Christoph, good. But how does it change? I mean, it's a trivial question, by the way, because
not linear. It depends on.
It varies randomly. That's all what I'm saying. By definition, how does it vary? It's the random variable. It varies randomly. يعني ما بعرف how does it. I will not know. It varies randomly, but within the shape of the distribution that I assumed. Let's say it's normal distribution, but it varies within that normal distribution. But on the other hand, a decision variable, yes, it varies because it's called a variable, and a variable by definition it varies. But in what ways it varies? It varies in a way that it's called decision variable under my decision, under my control. I decide that the value of this variable x1 is going to be 7. Why? Because I decided so. So that's it's called a decision variable. I decide on its value. However, this may not be the best action or thing to do or the best value, and then we'll see why in a second. Because I'm going to use that variable now, that decision variable that I decide on its value. For example, in the previous problem, or then still this problem that we're working on, the plier and the production problem for pliers and what was it? And wrenches and pliers. What are the decision variables for that problem, you would think? What are the things under your control? Let me go back to this.
The number of pliers and the number of wrenches.
Wrenches and pliers?
Yeah. Very good. Thank you all. That's what I decide on. I decide on how much to produce. I could produce 5, 10, 500, or none. Do I decide on the steel amount available?
No.
No,
we can't.
Exactly. So that's not a random variable. Okay, so that's good. So the decision variables at this problem are how many wrenches to produce and how many pliers to produce daily or weekly or whatever, monthly, whatever that period that we're looking at or studying. Okay, now I will use those two. I'm going to call it x1, let's say, and x2, or call it, let's say, variable w and variable p for wrenches and plier. Call it whatever you want to call it, but I will use those two decision variables to build an objective function.
Doctor?
Yes, sir.
How to define the amount of raw material required to produce each unit? I think is than the number of wrench and plier.
More important in what sense? What? I can't hear you well, ya Muhammad.
يعني need to, if we want to produce any range or any plier, in industrial sense, we need to know the amount of raw material required to produce each unit.
That's correct. That's correct. That's correct. That's correct. But yeah, we need to know that. But what does this have to do with my question regarding the objective function or the decision variables? The decision variables are, as I said, are defined as things that are under my control, which is in this case how much to produce. Now, as a consequence of that decision, will be what you just mentioned now. How much of steel on other raw material will be consumed by my decision, and then I will compare that to the available raw material. That's correct. That's part of the constraints. But so bear with me a second, and I'll get to that one. But before I get to that part, I'm saying that what is the objective of this problem? What's the goal? What's the ultimate goal? The ultimate. Okay, but thank you. Yes, is the ultimate goal to figure out how much raw material I'm using, or is the ultimate goal is to consume all the raw material that I have? No, I don't care about that. What do I care about?
To maximize our contribution.
Making money, obviously,
Yes.
which means I want to maximize. I want to make as much money as I can, which means in this case I have to somehow figure out a way, which is not very difficult now. Figure out a way to express that profit or money that I make as a function of those decision variables I just defined. So I have to do them in that order, by the way. First, I will define the variables, and then I will define the objective function. So in this slide, and this is the kind of data I was talking about last time that you need. This is, you put your arms around the problem, and then you collect the required data. And this particular case, I have collected all the data that I need. So, there might be some, maybe material cost or some other cost depreciation or things like that for the machinery. I did not include in my frame, so I drew the boundary only on this kind of data, and I'm going to use it. So that's why it's easy to solve a textbook problem rather than going around and collecting your own data to formulate the problem. Anyway, that's why we're doing the project. But in this particular slide, you'll see all the data that have been collected for this problem. And in this data, there's only two pieces that are useful to build the objective function, which reflects or represents the money that the company make. So if you build, let's say, W amount of wrenches, or W number of wrenches, then your profit will be 0.4 W, and if you build P pliers, then your profit will be 0.3 pliers. So the total you're making is 0.4 wrenches and plus 0.3 pliers, which I want to maximize. And finally, this should be 3, as a matter of fact. I don't know why it's 2. So 1, 2, 3. Just notice that, even though this slide is not new. Anyway, so the third thing is constraints, and then I'll get back to what Muhammad was saying a while ago, that now I need to express the amount of resources consumed by my decision. So if I decide to produce P pliers and W wrenches, how much consumption, raw material consumption, I'll start with the steel, for example. How much steel is being consumed by my decision? Let's see some answers, please.
It depends on the number of wrenches or pliers I am producing.
But I produced W wrenches.
W times 1.5
W.
Correct.
1.5 W.
مظبوط مايا. فإذا 1.5 W. طيب, if I from of what? The 1.5 W, that's the amount of pounds of steel utilized or used. Is this the total amount of steel used in this problem?
No, you have to add pliers.
For the pliers.
Okay, the total amount of steel used is
1.5 W plus 1 P.
Tamam. So that's amount. Whatever I do, I should not exceed this 15,000. And that's the idea of what I call constraints. It's these things in the problem that prevents you or constrains you from achieving an ultimate maxima. That means what prevents me from making an infinite amount of money? One thing for sure is I don't have an infinite amount of steel to make an infinite amount of pliers and wrenches to make an infinite amount of money. So these things that hold you back in general, things that hold you back from achieving an ideal maxima or an ideal minimum, in this case, what holds you back from making an infinite amount of money? Yeah, because I cannot make an infinite amount of and wrenches because I don't have an infinite amount of steel. Also, that's one particular angle to the problem. But also, I don't have an infinite amount of molding time or machining time or assembly machining time. Also, I don't have an infinite amount. And also, if I do that, I don't have also, I cannot sell more than 8,000. Also, these are all the things that hold you back. So all of these things are expressed under the constraints category. Those are the G functions that I was talking about. Somehow I have to express them mathematically. And it's not very difficult for this particular problem to express, but at least conceptually now I know what are these constraints which prevent you from making an infinite amount of money or prevents you from maximizing or minimizing your objective function to an extreme. Okay? I will come back and formulate this problem.
We have 5 constraints, right?
I'll go back to this problem later. Let me hold on to your thought, and then let me mention a couple of things, couple of terms that we will use throughout the semester. Important terms. A feasible solution. What do you think a feasible solution for this problem that I had? What is the solution for this problem that I just mentioned? Produce. Look at the numbers. Produce. I don't know. A feasible solution, that means it's a solution. What was a solution to this problem? One solution is produce nothing. What is it?
It's
Cannot hear you well.
It's a total number of wrenches and pliers, taking into consideration the set of constraints.
I'm saying what solution would be how many wrenches to produce and how many pliers to produce. The answer should be two different numbers, two separate numbers.
To satisfy the requirements or the constraints.
Obviously, to satisfy the requirements. That means that's a good add-on to mention, which satisfies the constraints. That's by definition a feasible solution is a solution for those x's, which is the decision variables. In our case, we call them x, we call them w and p. So it's a solution that does not violate any of the constraints. I have not articulated completely those constraints, but mentally we have talked about them. I will express them in a second. But I'm saying one solution that does not violate any of these constraints for sure is a solution where it says W is 0 and P is 0. Just produce 0 of both.
Optimized solution.
What is that?
But it's not necessarily an optimized solution.
Well, I didn't say anything about optimal solution. I didn't get to this. It's on the list. I'm still on bullet 1. A feasible solution, but you're right. But it has nothing to do with my question. My question is a feasible solution. What you see here is a feasible solution is any solution. It's a solution that does not violate any of the constraints. Obviously, if you produce nothing, you will consume nothing, and you will not violate. You will not use more than whatever 15,000 pounds of steel because you haven't used anything. Or you produce one of each is also a solution, right? It's still a feasible solution because it does not violate any of the constraints. That means I've used whatever I have, not less than whatever I have actually, not more. So in general, how many feasible solutions do we have? 4 or 5 for this problem?
Infinite.
More. Many.
7?
Infinite solution.
Infinite. Bravo. That was a trick question. Yes, we don't have 7 or 8. We have an infinite number of feasible solutions usually. Why? Because as I mentioned also in the previous few slides, that those fractional solutions are also acceptable. That means, P can be 0.5 and 0.51, 0.55, 0.57, 1.2. Okay, all of these are solutions. So that means I have an infinite feasible amount of solutions. For all the problems, usually if it doesn't have an infinite number of solutions, then it has no feasible solution. That becomes the problem becomes infeasible. I'll talk about that later. But in general, I'll have an infinite number of feasible solutions. I have so many values for W and P that will not violate the constraints. But all of these are called feasible solutions. Now, the set of feasible solutions is called a feasible space, which we will also see in the next few slides, but keep that in mind. All these feasible solutions, if I put them together, this is called a feasible space. And your job is basically to search for the optimal solution within that feasible solutions. So normally there is a unique optimal solution, a single one, which is a feasible solution, but ranks the better than other feasible solutions if I use the objective function as a ranking function. That means, if I plug in that feasible solution in the objective function, it gives me a better value than the others. So I can think of the objective function as a fitness function where it tells me, how good that solution is, or a goodness function, So I have a feasible solution. I plug it in the objective function, and the answer comes back to me, that this feasible solution is better than the other feasible solution because it's larger or it's less, depending whether I'm minimizing or maximizing. So 3 things we learned on this slide. A feasible solution is any solution that does not violate any of the constraints. There are infinite number of feasible solutions. The objective function acts as a goodness function for all of these feasible solutions. It ranks or weighs these various feasible solutions and gives me, from amongst all of these feasible solutions, I'm searching for one feasible solution from this set of feasible solutions, which has the greatest value of the objective function, which we call an optimal feasible solution. Okay? Now, going back to the problem that we started, we can quickly go over the formulation now. So the first thing, again, I repeat, the first thing we do, we define our decision variables. In this particular problem, I call them P and W. In the rest of this course, actually, I'm going to call them X1 and X2. I like X's to be the decision variables, but this is a special case now. We started with P and W, but this could be X1 and this could be X2. So it's a vector of 2. The solution vector or the decision variable vector. So this is one vector decision variable. This is the second decision variable, P. And I usually like you to spell it out, define it in plain, pure English, and be very specific about what do you mean by this P. It's the number of pliers manufactured, okay, in a week or a month, whatever we're looking at. W is the number of wrenches manufactured, okay. So that step, I defined in words my decision variables. Then I use these decision variables to build the objective function. 0.4 W plus 0.3 P, and I usually call it, I'm maximizing, so maximize Z, the letter Z. Okay, let me see. If normally I call it Z by convention, but Z, which is equal. I normally use the letter Z for the objective function, maximize Z or minimize Z, which is equal this. And I normally use X1 and X2 for decision variables, but now I'm using P and W. But from after this example on, I use X1, X2. So the next thing is what? After you define the decision variables, and then you build the objective function, what do? We build the constraint. And bravo. And then somebody asked me also, are there 5 of these constraints? He was kind of right, but wrong. Yes, there are 5 constraints, but there's also what we call the negativity constraint. That's the 6th one that I always have to remember, and it's very important to remember. But I'll get to it at the end. So let's start with the steel constraint. And as we already guessed, that the consumption of steel, turn off your mic, Ali, please. The consumption
I
of
just
steel.
wanted to ask. Sorry.
Go ahead. Yeah,
I
what's
wanted
your
to
question?
ask you just to go back to the table so I can take a screenshot just to see the problem again, please.
بشرفك. You have the slides. Download the slides and put them in
Okay,
front of
doctor.
you next time.
Sorry,
Okay.
doctor.
Right. Now, so the steel and the 1.5, we already formulated this function. So this is my first G1. This is G1, right? My first constraint. This was the F function, was the objective function. Now the G functions. G1 is 1.5 W. It says it consumes 1.5 pounds of steel to build one wrench. So if you build W wrenches, it's obviously 1.5 W plus 1 pound of steel for one plier. So plus P less than this 15,000 pounds of steel available. So that's the first constraint, very simple. The others are as simple also. A molding machine constraint. Each one of these products uses 1 hour of molding machine on the molding machines. That means W plus P less than 12,000 hours available. Similar thing, wrenches take 0.4 hour and the pliers take 0.5 hours. So in total, 0.4 W plus 0.5 P should be less than the available. So the right-hand side is always available. Remember, those are available meaning time 5,000. And then you have the wrench demand. You cannot sell more than 8,000, so W less than 8,000. You cannot sell more than 10,000 pliers, so P is less than 10,000. And finally, last, the non-negativity constraint. That means you cannot have negative values for P and W. You can have 0, but not negative. Or you can have 0 or positive, so we call non-negativity P W larger than or equal to 0. Every problem has this non-negativity constraint. From one problem to but the non-negativity always there, so do not forget to have it. So there's no this is, if you recall, the upper bound we call it, but there's no need to really distinguish that in particular, but those are really upper bounds on the decision variable, and this is the lower bound. Any questions so far? Okay, so this is the complete formulation. Yes, sir.
The last constraint, it will not affect our objectivity in this problem.
What does not affect which one?
The last constraint, the
Hey, what
non-negativity.
about it? Hey, Shubin, what about it?
يعني إذا ما حطيناها ما راح تعمل effect على الobjectivity تبعنا.
شو الobjectivity؟ ما بفهم شو objective function you mean?
Yes.
Well, it does, no, because it is a constraint. I mean, you may have some negative values of P and W, which is something imaginary. I don't know how can you have negative production, but you could have negative values of P and W that make the objective function large. I mean, not in this problem, obviously, but in some problems. You know what I mean? So no,
Yes,
I
yes.
mean, skipping these may result in the wrong answer. You may get a large objective function, but with the ridiculous answers for for the decision variables. You know what I mean? So in this particular
Yes, yes.
problem, yeah, it won't, but in general, it does. And I will see that also when we solve the problem. Why these two constraints are very important. These non-negativity constraints. Any other questions?
Thank you, Doctor.
Yes.
You're welcome. Yes, sir. One more question. Let's see who's it.
Yes. Ala is speaking. Constraint. We will assume them constant throughout this course, or they will vary in the future problems. Just this question.
Okay, I don't know what does that mean. Constant in the. I don't understand. Can you explain to me? So that's why I have to be very careful when you talk to me, and that's why you see, because
No, I
every
mean,
word is. What do you mean?
I mean the constraint.
What is constant? What about it?
For example, here the constraints for steel are 15,000.
This is not called the constraint. The whole thing is the constraint. The 15,000 is only the right-hand side of the constraint, and it represents the steel availability.
Okay, I mean, we might have an equation instead of 15,000 later, for example. That's my question.
Why? But why? Why? I mean, so you
يعني
will
for
have
example,
instead of 15,000 some weird equation.
no, for example, we can sell 8,000 wrench. Maybe if we export to another country, this number will increase. I mean, we will assume them fixed in this course.
Let me go back to this yeah. Yes, we will
For
assume
example,
them.
yeah, we will
This is,
assume that
I understand what you're
demand.
saying.
Okay.
Everything. Let me go back to this way here. Do you see this slide?
Yes. Okay.
You see this slide? I
Yes.
explicitly said linear program. These functions are linear. They look like this. No deviation from this. You see how the objective, the constraint looks like? AI1 x1 plus AI2 x2 and so on, less than, larger than, equal BI,
Okay.
right? And then the
Right.
next constraint will be, it will be A2. This is the first one, A11 x1, A21 x1 plus A22 x2 plus A23, so on until B2. And then these slides I said, all of these are known AICB, okay, with certainty. That means no, constant. See, these are very important slides. But now they make more sense after, you go back to them when you study, okay? So that's why
Thank
we
you.
follow that form. It's exactly that form, no deviation. So this is B1, it's 15,000, and B1 is constant. This is B2, it's 12,000, and it's constant. Do you understand? This is 1.5 and it's constant. So this is the C11 in that previous slide. Do you understand? So these and when I say deterministic optimization, this course is called deterministic optimization. What we mean by deterministic are these: the coefficients, the 0.4, the 0.3, the 1.5, the 15,000. These are deterministic, known with certainty, and we're using them to optimize this quantity. No, I want to make sure that most of you in this class had the same issue. I'm pretty sure, but now we explained it. So we're following this exactly as I explained it in the early slides. This is the mathematical program we're looking at. Now, scenarios where you mentioned, okay, I'm not answering only your question. I'm just actually using your question to explain more. Scenarios where you mentioned that you export and import, and you know what I mean? All of these could be formulated within this framework. Maybe you'll have another constraint that will express that scenario that you mentioned. Okay. All right. Now what we did here, just for this problem, recall here it's 0.4 W plus 0.3 P, because this is 40 cents and 30 cents, and we have 15,000 here. We're gonna solve this problem graphically. That means I'm gonna now draw a number line, and put these values on a line. And the problem is, if I do have a line, look, this is a number less than 1, and this is 15,000. So a number line that I'm going to use is going to be very weird, that I will be able to show a small number like 0.4 and a large number like 15,000. It's going to be a problem. So for that purpose, what I did, I said, let's make this in thousands, the formulation. So instead of having 15,000, so I'm making 15, and I'll multiply that by 1,000. That's all what happened in this next slide. Understand? And the reason for that is to make it simple for me to plot in the next few slides, because I'm gonna use the graphical solution approach first, which is done by plotting. Okay, so all what I did then, the 15,000, those do not change actually, because these are not quantities or thousand. These are just 1 pound of steel times that. So we're making now. So really, the definition now P is in thousands of pliers, and W is in thousands of wrenches. That's all. So the profit on 1,000 pliers will be $400 instead of $40 cents. That's all. You got it? Okay. Okay. Now we want to start looking at the graphical solution. Okay. Oh. a couple of things. Omar, next time remind me.
دكتور ما سمعتك sorry.
Next time remind me to make you a co-host.
Okay, I will.
In the beginning, so that if anything happened that disconnected or something, you take care. Plus, there are some people that are in the waiting room. Okay. 1 second. How can I admit these people? There are still some people in the waiting room, or left already. It locks by itself. How do I do that? 1 second. Okay. There are about what? How many people? 24, 22. So there are about 3-4 absentees. Hey, Omar?
4 absentees, doctor.
Okay. All right. Now let's continue.
But sorry, sorry. If someone just entered the meeting, can he please send me a private message لحطوا attendance لأنه هوليك already أخذتهم.
That's fine. It's no big deal. Yeah. Okay. So let's continue with the lecture. I see. So we're done with that. Characteristics of solutions to the LP.
Doctor, we're not seeing anything.
Oh, really? Okay. How about now?
Yes, we can see, doctor.
Okay, thank you. Okay. So how do we solve that problem, this production problem that we just saw? What is it called? GTC or something like this. And by the way, the Excel file for this problem is on Moodle already, but you will get to need it next week when I talk about Excel solution, okay? But it's right there. So how do we go about solving this problem graphically? And we only use the graphical solution for the optimization problems, or for LP, linear programming problems. For short, it's called LP, linear program of 2 decision variables. Okay, for problems that have more than 2 decision variables, we cannot solve them graphically, but we have to solve them using the technique that we will learn next, which is called the simplex method, that can handle or solve larger problems, any number of decision variables. However, the graphical solution that involves only 2 decision variables will be very helpful for us to understand how does the actual real method, simplex method, work. Okay, so we will learn this today, hopefully by and next maybe one day, which will set the stage for us to learn the simplex method. So in the graphical solution that deals with only 2 decision variables, as I mentioned, the first thing we do, we plot the constraints as equations. So we look at the constraints, we take all the constraints and we plot them on a 2-dimensional graph, and we plot them as equations. So those, from that step, will allow us to find what we call the feasible region, which is the feasible set, which I mentioned also earlier, that the set of all feasible solutions, the set that contains all feasible solutions, which, as you know, there are infinite number of them, that set is called a feasible set, and sometimes called feasible region when we look at it graphically. Okay, so we will be able to see or physically look at the feasible set of solutions, which we call the feasible region, and somehow we're going to use our math power to figure out from amongst all of these feasible points or solutions, what is the optimal solution. For that, we do what we call an isoprofit line, and then, which meaning that we plot the z function, the objective function, and from that we should be able to learn about where does the optimal point reside within the feasible region. So that's the recipe. Let's see how do we actually execute it for the GTC problem. We will construct the feasible region like this, and again, it works only for 2 decision variables, this graphical solution. For 3 decision variables, we don't do that. Okay, and then this is x1 and x2, or W and P, doesn't matter. You can call it x1 and x2. Okay, and now the first thing we do is we take the first constraint, which is this one. We make it an equation, so we make it equal instead of less than, and we plot the line. Do you know how to plot a straight line? For those of you who don't, and you should be able, that's even less than high school math. Quickly, there are many ways to plot a straight line. An easy way for me is actually to assume, locate 2 points on the, locate 2 points and then connect them. So the first point is when W is 0, P becomes 15. So the first point is W0, P15. That's the first point for this line, and that's the point. W is 0, P is 15. And then the second point, I will assume P is 0, and then I will solve for W. So I'll have 1.5 W equal to 15. That means W is 10. So then I have the second point, 10, 0, which is right here. Then I will connect those 2 points with the line that you're looking at. Okay, very simple, straightforward. So I have one line, which is the constraint as a line. So the question is, since this is not a line really, this is an inequality. It's less than or equal to 15. So an inequality actually is not a line, it's a region. Maybe before I've done any of that, I should have mentioned this one thing. And this is where the non-negativity constraints that we discussed 5 seconds ago and play an important role. Imagine that this whole slide, actually, let me go back. And this whole slide, yeah, an empty slide, the whole thing is your feasible region. So it's the space. It's 2-dimensional space because we are only considering 2 decision variables. So everything is expressed in this 2-dimensional space. Now, the value of x1, p, or and w could be anywhere in this space. Okay. So, and to make it simple, what we do, we draw this. Those are the negatives. That this is a positive for, was it p here or w here? I forgot. It doesn't matter really. Let's say p here. W
was w on x.
So w was here, right? P here. Eh?
Yes.
Okay,
Yes.
thanks. So it doesn't matter then. But and this is negative and this is positive. So anyway, the value of P and W could be anywhere in this space. But since we said they cannot take negative values, automatically we excluded this. So they have to have jointly positive values. That means this is the only quadrant. You know, the upper right quadrant is where the solution will lie. We excluded all of these automatically. So applying, let's say, the non-negativity constraints right away as step 0, let's say, will tell us that the solution lies in this right upper right quadrant, the positive quadrant. Okay. Now, after saying this, I can start with what I just said. That's why I started with this quadrant now, and I am plotting the first constraint. So I think what I should do, mention this before I actually get to the step where I plotted the first constraint. Okay, now I have this first constraint, and then the question is, what did this constraint do to the region? And again, remind you that our region was this quadrant, the whole quadrant only. But that line divided it into two spaces, this triangle and everything else in that side. Is that correct?
Yes.
Okay, so now, which region is it? The triangle or everything else is the a region of interest to me?
It's a triangle.
So in order to know, thank you. In order to know, I normally have to test a point either here on this region, and if it satisfies this point, the constraint, then this is the correct region. And if it doesn't, then that means the other region is the correct region. Or I can do the other way. I take a point in this region, I will test it, but I need to know the coordinates, obviously, plug them in this constraint. If it satisfies the constraint, then it's okay, then this is the right region. Otherwise, the other region is the up. This is the strategy, correct? How do you know it's this one? For those of you who told me this is the one, how did you know? Mentally, without trying any points. Ryan Hamdan.
Yes, since it's less than 15.
عشان تعطي لي بيض؟
No, since it's less than 15.
ايه شو؟
Since it's less than 15.
شو يعني since ما فهمت شو since less than 15.
And 1.5 W plus P is less than 15, so we choose the triangle.
يعني هيك انت يعني your gut feeling, yeah, but what happened is mentally you took a point. يعني
no, since W and P have two positive coefficients, we can choose these.
Okay, thank you very much. What I do for those who are like me, they have to check. I take this point is in the 0, 0 is in this region also. Okay, I don't have to take a hard point like this where I don't know the coordinates of it at that point. I mean, I could, but I just have to figure out, you know, I can take 2, 2, this point, or 2, 4, or I mean 4, 2, this point. It doesn't matter. But why should I take these numbers? I'll take a simple point like this, 0, 0. It's at the boundary, correct, but still in this region. So 0, 0 is very simple. It will show me 0 is less than 15. That's correct. So that means this is the right region. Okay, so it's made in yellow now. So basically, this whole plane was divided into 4 quadrants, and I took the upper right quadrant. Even that quadrant now was divided into 2 subspaces, and then I took the yellow subspace. So now, all that I'm trying to show, I'm trying to close on in the set of feasible solutions. Now I know there's no feasible solution going to lie here or down there, but I know it's going to lie somewhere in the yellow region, but I'm not done yet. I have another constraint to use to plot, so that W plus P equal to 12, which I will plot as an equation first. And as I said, this is very simple to plot, but still, you know, if W is 0, P is 12. If P is 0, W is 12. So you have 0, 12, 12, 0 as 2 points. This is one. This is 1 point. This is another point. Now let's connect them. So look what happened. That constraint even ate into the yellow region a bit. So now we have 2 regions. This one below the blue line and above the blue line. Which one is the correct region? This or that? I use the same strategy.
The bottom region.
Below the.
I use the same strategy. I take that 0, 0 being in the yellow region, the below yellow region, and I say 0 plus 0 is less than 12. That's correct. That means this is the right region. This one below the blue line. So I chipped away this little area here. Okay, and end up with now the blue region as my feasible region that contains the feasible points or solutions. I continue plotting the third constraint using the same thing. If W is 0, what is P? P becomes, I plot this as a straight line, obviously, with an equality constraint. So if W is 0, P is multiply by 2, P becomes 10, right? So you have the first point is 0, 10. The second point is 12, 0. So you see this constraint. Also 8 into the current feasible region. And again, I have to check whether the yellow region below the blue line or above the blue line is the region of interest. Taking 0, 0 as my checking point will tell me that it's the one below. So it's this one. Again, it chipped away a little bit from the region. So here asking what happened to the constraint W plus B equal to 12, this one. This one. What happened to that one? Hey guys? Hello? Let me read
We
some
have
words.
multiple constraints, so we have to satisfy them all.
That's correct, but we do have to satisfy them all, and this is satisfied because it's below, everything below it. Really, this constraint, because it does not impact the feasible region, it's above it. In a way, it is a redundant constraint, so it doesn't matter whether we have it or not. It will not change the solution of the problem. Okay. So with or without this constraint, this feasible region is going to be the same. That's what I meant in here. So it's called a redundant constraint, or maybe a dominated constraint. That means this constraint was dominated by other constraints. Okay. Now this is the new feasible region. Do we have more constraints to plot? Yes, we have the W less than 8. It was the 8,000, but since we made it in thousands, so it's W less than 8. So we have this line over here, W less than 8, just a vertical line and a horizontal line. They chip away from that region, only the yellow part is at the boundary, it didn't matter. Now we have all our constraints, and this is the final feasible region. Yes, sir.
So P less than 10 is also a redundant constraint.
In a way, yes, it's right there at the boundary. Yeah, it didn't matter whether we have it or not. It will not have changed this current solution, but we will discuss sensitivity analysis later. That means, what if I was mistaken that 10,000 was 9,000 instead? What will happen to the optimal solution? And that's called sensitivity analysis when we play this game of what if game. We will get to this next lecture. Okay, so that's why, now it doesn't matter, but later it will matter that P equal less than 10 on constraint. Okay, so now, okay, the yellow region is the feasible region, and that means all my feasible solutions fall in that yellow region, which means you pick any point in that yellow region, any point blindly, it will satisfy all the constraints. That means it's feasible, because by definition, this is the feasible region. So any point blindly will satisfy. Anyway, it's 5:12. I didn't know that. Right. I need to wrap up. I have some other class at 5:30. So what will happen is we'll continue from this point next time. Okay, figuring out. Okay, so what's the optimal point? If I know now these are all the feasible points, fine. Where is the optimal point? Which is one of these
intersection between constraints.
I don't know. We'll keep it a surprise for next time. All right. See you next week. Have a great weekend.
Thank you, Doctor.
Can I have a question, please?
Thank you.